Hello and welcome to this A-level computing lesson. And as you can see from the title, we're today looking at Boolean algebra and specifically looking at logic gates and truth tables. And this is an introductory lesson to this topic. So if we look at the A-level spec, and I've got it up here, let's just reflect on what we've been looking at recently. We've been looking at, we're in 1.4, data types, data structures and algorithms. We were looking at data types and we've done some of this topic. We did the first few little things in here looking at representation of binary and hexadecimal, and we looked at sign magnitude and 2's complement. And we're going to skip quite a lot of the topics in here because they are full A-level topics. We're not going to look at 1.4.2 because those are programming topics and they're not covered in this part of the course by me. And we're going to focus instead on 1.4.3, which is Boolean algebra. So we're going to begin with a little introductory kind of chat about what Boolean logic actually is. But before that, let's just do the learning outcomes for the session. This is what we need you to pick up. You need to understand what is meant by Boolean logic. Understand how to create a logic diagram based on a Boolean expression. Understand how to create also a truth table based, I should say, on a Boolean expression, and be able to write a Boolean expression from a given truth table. And it might be, hopefully it should be, that those terms are things that you came across at GCSE computing level in year 11 on unit 2. And to be honest, most of this lesson really is just about at the year 11 level. It's only the A2 topics on Boolean where things start to get a little bit more challenging. So let's just have a little think. Oh, finally understand how problems can be defined using Boolean logic. So that's a slight difference between GCSE and A-level. We're actually going to be looking at using Boolean to define problems. So let's have a little think, first of all, really about what Boolean logic actually is. And we've got a quote here from Boolean, from a man called George Boole. And on the principle of the truth classification, we want no longer to associate logic and metaphysics, but logic and mathematics. Now, George Boole, who we're going to look at shortly in a minute, that came from a publication of his mathematical analysis of logic back in 1847. And originally, logic was really something that was associated with the idea of philosophy. In Western culture, it was Aristotle who first proposed the idea of logic. And indeed, logic derived from the Greek word meaning the word. And indeed, it was Aristotle again who developed the theory of syllogisms, which we will look at in year 13. And there are other philosophers that we could look at, Plato, some Chinese philosophers, who also explored the idea of logic. So really, it was George Boole that took it away from being a philosopher, something we explored within philosophy, as to something we explored in mathematics. So this was George Boole. He was an Irish mathematician. And it's after him that Boolean logic is obviously named. And essentially, it's a method of expressing a logical problem in a symbolic format. And this work really came to be, excuse the pun, symbolic or kind of important in terms of computing in 1937. Somebody called Claude Shannon applied his work to the design of actual circuits. And then when circuits were created, algebra became the foundation of all digital circuit design. And Alan Turing was able to implement these ideas himself in the early days of computing, all about that. So it's also worth remembering that even in the early part of the 20th century, mathematics was not well regarded in comparison to science as a field of study. There was still people slightly sniffy about the study of mathematics, and it was really after these discoveries and Turing's discoveries that mathematics was looked on in a new light. So it's important in the birth of computing means that this is no longer the case. His ideas, I would say Boole's ideas about logic, gained him admittance to a real select group of people who could be regarded as computing pioneers. So you're looking at the likes of Charles Babbage, Ada Lovelace, Claude Shannon, we've just looked at, John von Neumann, Alan Turing, Tommy Flowers. So it's not an exaggeration to say that without these individuals, you would not be looking at a video about this on a computer. So really, really important in the birth of early computing. So on with how it actually works. We know that in computer science, this is something we're familiar We know that computers are made up of millions and millions of switches. We know that we're not really talking about quantum computing here. We're working on the principle that switches can have two values only, on or off. And we know, because we've explored this with binary, that the on and off values can be used to generate off would be 0 or false value in Boolean, and 1 might be a true value in Boolean. So that's really, we're already familiar with that concept from the point of view of looking at early binary. And then how it works is that we can group these values. These individual binary values can be grouped together, and then they give us binary numbers. But what we're really looking at is concerning the process of using Boolean logic to compare and evaluate these values. And we can also use logic gates as something called an input mask, actually, which is something we'll look at in year 13. But it's these values that are compared when computers are performing logical operations. So, for instance, if you're writing a Python program and you're using an if statement, you're using the principles of this logic to create that if statement and perform that test. So, can you see in this pretend hangman program that we've got an extract from a hangman program, can you see where we've applied Boolean logic here, just in a regular Python program? It's actually here, we've got a true value here, and our while loop is controlled by a true value. So play again is a Boolean variable, and then we've got an if statement here. If replace not equal to y, and then again we've got play again equals false, so another use of a Boolean variable there. So that's really quite common usage. So Boolean is something that you will have come across, even if you haven't considered it as being a branch of mathematics while you were doing so. So these are the gates that we need to look at, or that as part of A-level computing. And if you'll hopefully remember 3 of these from your studies at GCSE, and you will have noticed that there is a 4th gate which you will not have looked at previously. So each of these logic gates performs a different function. They all have a different role, and each logic gate has at least one input. So it would look at least one input coming into it, and all of them would generate an output after the input has been evaluated. So not an and, an or, I'm hoping you've come across before. XOR is maybe one that's new to you. And then what we can do is we can express all the possible inputs and outputs for each gate in something called a truth table. And again, you will have done truth tables at GCSE level. So let's have a look at the 4 gates that you need to understand. And it's worth remembering, by the way, there are some additional gates in Boolean logic that you do not need to know for A-level. You'll only ever get asked about the 4 that we'll look at here. So the first one we're going to look at is a NOT gate. So NOT gate basically takes whatever the input is and inverts it. So it turns 0 to 1, or if the input is a 1, it turns the 1 to a 0. So here is our input, and we express that in terms of Q. So Q is not equals not A, and there are some symbols that you need to start to get used to as well. Here is the symbol representing not, so Q is not A. And in terms of a very, very simple, it's the easiest and simplest truth table to draw. Here it is, both the possible input values for A, 0 and 1, and both the possible output values for A, which are 1 and 0. So if it's not 0, it must be 1, and if it's not 1, it must be 0. So not is a really, really straightforward one to do this with. And is different. This time you'll notice that there are 2 inputs, and the AND gate compares both inputs, and it will return a true value, or a 1 if you like, if both inputs are true, and both of them must be true. So both of these values must be 1 or switched on if we're going to generate a true value. So this is what this looks like. Q equals A and B, and again we've got a symbol that we can use to express this, and again get used to the use of that symbol because you will see that used in questions. And here is a truth table for an AND gate, and you can see there's only one circumstance where we would have Q being 1, and that's where A is 1 and B is 1. In all other circumstances, it's set to 0. Even when both of these values are the same, they're not true. So it doesn't generate a true output. That's the AND gate. Or another way of referring to that is actually inclusive OR. OR is just fine. You don't have to call it inclusive OR. OR compares both of the inputs. Again, there are two inputs, and it returns a true value if either or both of the inputs are true. So as long as there is one true value between these two inputs, you will get a true value as an output. So Q equals A or B, Q equals A, and here's the symbol for OR. In fact, you don't need to have that little underlining under it. You can just almost have it as a V shape, A or B. And again, you can see this time, very different to AND, it's actually true in all but one circumstances, because in all these circumstances except one, there was at least one true signal. So here in the first instance, when there are no true inputs, both of the inputs are set to 0, the result with Q has to be 0. Here B is true and A is false, but that's okay because we only need one. The same here, this time A is true and B is false, so one's true, so that's fine, we get 1 then. And this time they are both true, but it's still true to say that either or both of them are true, so that becomes true. And in the new one, which you may not have seen before, is exclusive OR. And it's very slightly different to OR. This time it compares both inputs just like previously, but this time it only returns true value if either input is true, not if both of them. So this time you've got AX, or in fact we should have had the underlining on there, but never mind. A or B, so that's going to be false. This time B is true, so we can put a 1 there. This time A is true, B isn't, but we've still got one value, so we can put a 1 there. At this time, both are true, and this time that generates a false value because it's if either, not both, are true. So those are our 4 basic circuits, and you need to be comfortable with 4 basic gates, and you need to be comfortable with how each one of those works and be okay with drawing a truth table for each one. So what we're going to do, in fact, what I'm going to do now, before we get on and start looking at the next kind of set of examples, is I'm just going to show you a really useful little program that you can use to help you create truth tables and to create logic circuits and to be able to help you answer the questions that we're going to do. If you already know how to use this question, what I'm going to show you, which is called Logically, I'm going to put a link at the top of the video, and you can just click on that and it should take you past this section of the video, so you don't need to follow it if you don't need to. So we're going to look at a program called logic.ly, which is a great way of practicing creating logical diagrams. Okay, so this is logic.ly, and it's a piece of software which you can actually download or buy, but we don't need to either download it or buy it. There's an online version which we can just try, and I'm going to demonstrate how to use this to create very simple, or more complex actually, logic diagrams that you can use to help you when you're learning this topic. So I'm just going to click try online, and essentially it gives us, let's just close that. It gives us a series of things which you can use as inputs, outputs, a variety of gates, and some things called flip. We're going to look at what flip-flops are in year 13 and some other symbols as well. So it's really easy, it's just drag and drop. So let's just, for instance, do what a NOT gate might look like. So you can see here we've actually got a NOT gate. I can just drag that onto the canvas like that. I can zoom in, whoops, I can zoom in a bit, I can make that a bit bigger. And if I want to, I can just drag the screen there so we can see it. And what I want, you can see there's one input going into it and one output coming out from it. So I want a switch. So I'll just drag a switch there, and I can connect the two like that. And now I've got a switch which I can actually toggle, and then I've got a light bulb which I can use as my output, and I can just attach that to there. And you can see on, off, on, off, on, off. So that gives you a practical demonstration of how a NOT gate works. And it's exactly how we said it was. When the gate is off, the light is on, and when the light switch is on, the light is off. So it flips it, it inverts it. Let's just do another one just so you can see what it looks like with 2. So we could have an AND gate here. I'm going to stretch, and again I'm going to go, this time I need 2 switches. So just drag one switch, connect it, and see how easy it is. I just drag the connector to it, and then I put a light bulb there again. So this time what you'd expect, we've got both switches off. So if what we said was true, you would only expect that light to come on if I turn both these switches on. So I turn one on, the light hasn't come on. Let's turn that off and try the other one. Well, that one still hasn't worked. Let's see what happens when we try them both. There we go. So you can see this is a really effective and simple way of modeling the truth table, the circuits that we've just been looking at, that we've just been looking at. We'll do one more because I think you're probably getting the hang of how it works. Let's just try an OR. So OR, we want a switch here, and then we want another switch there because most of these gates have 2 inputs, and again a light bulb. So now we would expect this to work if there is any of these values are true. So at the moment they're both false. Now I've got 1 true value, 2 true values, 1 true value, and in all those cases the light comes on, turn them all off, and it works perfectly. So those are really, really simple. Obviously at A level you won't actually be answering questions really with diagrams that simple. We will need to produce 2 or 3 level truth tables and diagrams, and we're going to go back and have a look at how to do that in our presentation now. But I would really recommend Logically. Logic.ly is a great way of practicing this and seeing how you can test the circuits that you create to make sure that they work and that they're right. And you will, I think, find it easy to understand this topic by using this tool. Okay, so you can straight away see here that we've got a much more complicated looking expression. We've been working with nice simple individual gates up until now, but now we're looking at something considerably more complicated, and this is the kind of thing you're going to need to have to be able to cope with. It's really actually quite straightforward once you've got a bit of practice. So we've got Z equals not R or S and T. And what we're going to do, we're going to have a look at how we would solve that. I'm going to build it up bit by bit. I've already done this in Logically, and I'm going to show you as we go along how each part of this might look and how you might approach the solving of this particular problem. So the first thing, we're going to build it using Logically. So this is a really good way of actually doing a practical implementation of some of these theoretical questions. So the first thing I want to do, the first bit is Z equals not R. So that's pretty straightforward. That's pretty easy to build. We've seen how to build that already. There is R, and you see I've created a label. I should have shown you how to do that. You right down the bottom there's a text label option, and I've just done not R. There's the not gate, and there's our output. So that works perfectly well. So that's the first bit done. Then it wants us to OR that, so it's saying not R or S. So I've built an additional gate into this equation now. So you can see there's my not R there, and then I'm saying, right, whatever the result of that is, I need to OR it with S. So there is my S input, and I've connected, that's one of my inputs into the OR gate, and the other input into the OR gate is whatever I got as my output of not R. So now I've got not R or S equals Z. And the last bit now, what I need to do is I need to do an AND to get the overall result. So the last part of that, we've now added a third switch, T, which gives us our third input, and as it's an AND that we're doing, we know that we need 2 inputs. So T is going to provide us with one of those inputs, and the result of our other equation is going to provide us with the other one. So that's what you get. That's how you can express not R or S and T as a circuit, and how you can do that in Logically. So that's hopefully fairly straightforward. What you might want to do is pause the video and try and build that yourself. You might want to do it with the stages that I did and just recap those last minute or so of the video just to make sure that you understand it. Because what we then need to look at is how do we do this as a truth table. So the truth table is actually relatively straightforward, because if you've been able to do the previous part of this, you should be okay with the truth table. So the first thing we remember is this time, if we go back and look at the truth tables we did before, you can see that in each case there's only 2 columns for the inputs, because we're going to have two inputs and 1 column for the output, all except for not, where there was only 1 input and 1 output. And already obviously it's a more complicated circuit, so it's obviously going to be a more complicated truth table. So if I've got 3 inputs, I need to put all the possible values that those 3 inputs might have together in a table. And so if I've got 3 possible inputs, then that means I can go all the way to 7 in binary. That probably doesn't make sense to you, but if you think about it, all the possible there are 8 possible sets of value that I can represent in using these 3 inputs, going from 0, 1, 2, 3, 4, 5, 6, and 7. So all I then do, what I would do, when you see people do truth tables, some of the time they might omit these intermediate stages. You don't have to include them, but I'm doing it because I think it's easier. So we're going to do the same process that we did before. So the first thing I'm going to do is I'm going to not the R. So I'm only looking in this column. So this part is not R. So I can see that all I've done is I've inverted the values in the R column and put the output in this column. So all the noughts are 1s and all the 1s are noughts. So that bit's very, very straightforward. So I can now do what I did before when I expressed it as a circuit. I can now do not R or S. So this time I'm evaluating the results in these 2 columns. I need the S column and the column that I just created. So all I'm doing is applying an OR to both of these values. So that means obviously anytime there is a 1 in either or both columns, I'm putting a 1 in as my answer. So that should work out as 1, 1, 1, 1, 1, 0, 0, 1, 1. If you check that, the only situation where we've got a 0 are these 2 rows here, and in each case that's come out right. So then the last stage, you'll probably be able to work that out yourself. And again, it's probably a good time to pause the video and just see if you can finish it off, and then come back in a second when I'll have filled in that right hand column for you. And there is our answer. There's our complete column. So again, what I've done is I've taken not R and S, which is that one, and I've taken T and I've applied an AND. So I've just compared those 2 columns only and recorded the value accordingly. And that way it's really straightforward that way, rather than if you don't put the intermediary columns in, you can work it out in your head, but I certainly find it easier myself to put all the intermediary stages in there. So all I've ever got to do is compare 2 columns with each other doing a simple shift. So it's relatively straightforward. So let's do a little practice question and see if you can work the answer out. And you'll notice that just to challenge you, I've written it in using the symbols that I've tried to teach you in the first part of this video. So you might want to pause it, and your first job is to try and translate what that means in terms of and, or, and not. And I'll show you the first part of what you've got to do in a second. Right, so that's what you should have. That basically means Q equals R or S and not T. So what I need you then to do is to see if you can draw for that a logic diagram. And again, I've done this in logically. I've already had a go doing it, and I'll put the answer below there in a minute. Pause the video, see if you can either create it yourself in logically or do it by hand and see what you get as an answer. So there we go. There is the answer that we've got. R or S and not T. So here's our R input. Nothing's happening to that, it's all on its own, so we just connect that to the OR gate, and then we're ORing it with an S and not T. So here's our T, we NOT it, and there's the other input into the AND gate. We AND that value with with our value in S, and that output provides the second input into our OR gate up there, and then we can turn the light. You can see in this case that the light works. Hopefully you've created a circuit that looks very similar to that and works, and what you could then do, if you, as a good bit of practice, is go on and try and produce a truth table for that circuit. So here's a little activity for you to do. I've done a few more of these, starting with a really simple one. Here's one which is just going to 2 levels, yeah, where you've just got 2 gates to compare in these 2, and then we've got slightly more complicated ones as we go down to the bottom. So what I would suggest that you do is have a go at doing this again, use it logically if you want to, produce a truth table for each one and use logically to check your answer. We're nearly at the end now, so this is a good time to pause and maybe come back and finish the last part of this video shortly. So the last bit that we're going to do is to think about how we can actually define problems using Boolean logic. And here is an example. In fact, this almost kind of takes us back to the very early days of syllogisms. So a car uses a logic circuit to decide whether to start the engine or not. The car has 2 buttons labelled S for start and D for drive. Very realistic, this, I'm sure. If both buttons are on, the engine will start. The engine also starts if switch I is turned on. So it's just written in normal English, and we need to define that in the terms of Boolean logic. So this is how we might actually do that. I've created a very simple table, and you can see that I've got 2 rows for each of my inputs. So there are 3 inputs. There's the S, which is the start button, D, which is the drive button, and I, which is the ignition switch. And those are my 3 inputs. And obviously whether the car starts or not is going to be my output. And it either starts or it doesn't. So it has 2 possible values. So in each case, each of these inputs can have 2 possible values, can't they? Because they're switches. So either the start button's on or it's off. Either the drive button's on or it's off. Or the ignition's on or it's off. There isn't an intermediary state. So do you think that you could create a diagram to represent what that looks like? So again, I'm just going to leave it here. You might pause it on this screen. See if you can create the logic circuit to express that problem. Right, so let's have a go at doing this. So first of all, I've written this out now as a Boolean expression. So I've used Z just because, and the way this works, obviously, it's going to be it's S and D or I, because the problem says to us if the switch, I can't remember what S was, the start button is pressed and the drive button is pressed, that will turn the engine on, or if the ignition switch is pressed, and that gives us that. Hopefully that makes sense to you. If not, obviously go back and recap some of those bits of the video that you haven't seen. What I would say to you, if it does make sense, is for AS or something for year 12 work, this is as far as we go with Boolean algebra and Boolean logic. In fact, no, we're going to look at something called Cairo maps next time, and we're going to look at simplifying Boolean expressions and finding ways that we can make them easier to look at. But what you might want to do is go and have a look at chapter 41 in the book, and there were some questions on page 227. If I were you, I would actually go ahead and read, 40, not chapter 41. I would read that chapter because it corresponds with what I've gone through in this video, and then try the questions on page 227, and then I can mark those for you or I will also post an answer sheet for you, and you can self-check those. But hopefully that's all made sense to you. What you should have found is really there's very little extension from what you've already done at GCSE. So that was an introduction to Boolean algebra in terms of logic gates and truth tables. I'll see you again soon.